All right, so last lesson is on what we call L'Hopital's rule. It's either spelled like this or it's spelled El Hospital, but it's pronounced L'Hopital. It's a mathematician who discovered this, and it will help us find limits. Okay, now this is unrelated to differential equations. It's unrelated to U substitution. It's just something we need to know for this class and before we take our midterm. Okay, now let's recall limits. Limits is all about what our function value is approaching as our x is approaching a value. Even though I do not have a defined function value over -4, my function values are approaching the y-coordinate of this undefined value, which ends up being at 2. So I would say that the limit as x approaches -4 of this function is 2. If I ever have a jump or an asymptote and our y-coordinates are not approaching the same value as an x is approaching a value, you'd say the limit does not exist. As x approaches 1, the limit does not exist. Okay. Now here at 6, we have a limit and we have a function value. They're just not in the same spot. So we'd say the limit as x approaches 6 of the function is 5, but f of 6 is 2.
Didn't you say for f of 1 is 6?
Oh my goodness. Yeah, thank you. I said does not exist and I wrote that one. Crazy. All right. And usually when we ask questions about limits back in Unit 1, we focused on these interesting locations, these jumps, these holes, these asymptotes. But in reality, if I asked you a limit question, say here as x approaches 0, and maybe I didn't even put that dot there, but I just said, what is the limit as x approaches 0 of this function? Well, our function value and our limit would agree, and it's equal to 4. And we talked about the function being continuous at that location because the limit and the function values agree. Okay? Typically, and I guess I'll say f of 0 is 4. Typically, limits equal function values. And if limits equal function values, we say the function is continuous when that occurs. Okay? Today, I'm going to give you some limit questions in this form. The limit as x approaches a number of some function. Okay? Well, if we have like a continuous function like x squared plus 2x, and I'm asked to find the limit, it's just as simple as finding the function value. 9 plus 6 is 15. This limit is just 15. That's it. The limit equals the function value. If I ask you the limit as x approaches pi over 2 of the sine of x, it's just going to be the sine of pi over 2, which is just 1. It's just the function value. Okay? But let's look at these two. If I tried to find the function value for this guy at 3, I would get 0 over 0. Now, we should remember from Unit 1, I talked about if our function has a 0 over 0, this is an indication that there is a hole. And we remember that for holes, our limits exist. Here at the location of this hole, the limit exists and is equal to 2. Here the limit exists is equal to 5, right? So for this guy, the limit exists. And this is going to equal a number, but I don't know what it is because I don't know that I can't just plug in the function value. If this guy, I try to find f of pi, I get 5 over the sine of pi, which is 5 over 0. If you end up with a number over 0, that is an indication of a vertical asymptote. Which means the limit does not exist. You're not approaching the same value to the left and to the right. So we can just say this does not exist. I don't have to worry about that. But we're going to go back and we need to figure out a way to do this. Okay? And most of the limits asked on an AP test will have these 0 over 0. And in AB calculus, we spend a unit worth of time talking about the algebraic methods that can be used to find those limits. Okay? And it's a good way to practice your algebra skills, but here in BC calculus, we don't have time to do that. And I didn't teach you these algebraic methods because there's an easier way. And once we know this way, we kind of can forget about the algebraic method. So it's like we kind of just get straight to the point here in BC calculus, and you only learn the stuff that you really need to know for the course and for the test, okay? And here's how we're going to tackle this. Let's go back to this one, this e to the 2x minus 1 over e to the x minus 1. It appears that this has a hole. I get 0 over 0, right? Well, I'm going to graph these two functions. You guys can do this if you have a calculator. If not, you can just watch. What? E to 0. Yeah. Yeah, you got it. All right. So I'm going to graph the function y equals e to the 2x minus 1 as well as e to the x minus 1. Okay, and it turns out these points, these graphs both have the point 0, 0, and it helps us when I do this demonstration that it has the point 0, 0. But if we don't have the point 0, 0, it would be fine, okay? But since we do have the point 0, 0 shared, I'm going to go ahead and zoom in to both of these functions as x is approaching 0. So I'm literally just going to zoom in at 0, 0. Okay, so this is e to the 2x minus 1, and here's e to the x minus 1. And I'm going to zoom in again. Enhance. Okay, there's my first one, there's my second one. And I'm going to zoom in again. And there's my first one. And there's my second one. When I zoom in enough around an x-coordinate of a function and the y-coordinates, what do the functions look like? They look like lines, right? Well, since we're talking about just x approaching 0, I'm talking about values that are infinitely close to 0 that I'm plugging into e to the 2x minus 1 and e to the x minus 1, right? So instead of worrying about the shape of this curve, why not just think about the equations of those lines? And instead of using e to the 2x minus 1 and e to the x minus 1, why don't I just find the equation of the lines? I'm going to say instead of these guys, use those lines. Now, what would be a good way and an easy way to find a good close approximation of those lines around 0? What could I use? A tangent line. A tangent line is going to essentially approximate our function right around those locations. And instead of using the curves, let's use the tangent lines. Not just lines, but tangent lines. So I need a point. Well, fortunately, both of these have the point 0, 0. But I also need a slope of those lines. The slope of those lines is going to be the tangent slope to the function at 0. So I'll take the derivative of e to the 2x minus 1, and I'll plug in 0. And I get 2 e to the 2x. At x equals 0, I get 2. That gives me the equation for the tangent line to e to the 2x minus 1. It'd be y minus 0 equals 2 times x minus 0, or y equals 2x. And let's do the same thing for the other one, e to the x minus 1 at 0. And I get I just get e to the x. At x equals 0, I get 1. And I get the equation of that line is y equals 1x. Well, this I couldn't find. I got 0 over 0. But this, sure, if I plug in 0 into the top and 0 into the bottom, I get 0 over 0. But what is this screaming for me to do? Right, cancel these x's out, and boom, I get 2. Now, if I had a calculator, I can confirm that 2 is the correct answer. How? Using this function. No, I wouldn't find the intersection. No. How can I confirm, using a calculator, that the limit of this is 2? Any other ideas? No, that'd find me the derivative, but like I kind of did the process that enables me to not have to use my calculator, but I can quickly and easily find this limit using my calculator. How? Graph the function, plug in values close to 0. Okay, so let's do that. I'm going to go and say, all right, well, what does e to the, I need parentheses, 2x minus 1 over e to the x minus 1 look like? Let's go back to Zoom Standard. Turns out that function looks like that. And if I looked at 0, I noticed the y-coordinate is missing, right? Now what you can't tell here, because we're graphing all of the points close to, is that there's a hole there, right? Which means there is a limit. Well, I could press trace and plug in 0.000001. And my calculator can quickly plug those that point into this and get a value which will not be a 0 over 0. Turns out it's going to be something very close to 2. It's probably not exactly at 2. It's the calculator rounding. I could do negative 0.0001, maybe a less amount of zeros, and see that approximation. Okay? So we did it. Now, what was very helpful about this example is that we had the 0.00. If we did not have the 0.00 and we were focusing at different locations, we would need to use these entire lines, and we would need to kind of look at things a little bit harder. But L'Hopital looked at everything really hard and discovered that you actually don't need the equations of the tangent lines. Turns out You just need the slopes of your tangents. And the slopes of your tangents to functions will give us limits of functions. Okay? So L'Hopital said, hey, you're trying to find a limit as x approaches a number or infinity of some quotient of things, and you get that f of a over g of a is equal to 0 over 0, or infinity over infinity, or 0 to the 0, or a bunch of other different ways, but really we're just going to stick with these two. He discovered that finding this limit is actually going to be equal to the limit as x approaches the same value of the tangents to those functions. So it's just the tangent slopes to the functions, which will just be equal to f prime of a over g prime of a. Piece of cake. 2x over 1x. That's easy, right? It's 2, right? What's the slope of e to the 2x at 0? 2. That's easy. Now, if this is 0 over 0 again, well then you could say, oh, this is equal to the limit as x approaches a of the derivative of that. And you could keep taking derivatives until eventually you can find a value. Okay? Let me prove it to you. Let's go back to x squared minus 9 over x minus 3. So go back in your notes to this one. You're trying to find this limit. Again, I could find this limit if I had my calculator by graphing x squared minus 9 over x minus 3 and plugging in values very, very close to x equals 3. I can see at 3, it looks like I have a function value, but it turns out at 3, I do not. I have 0 over 0. But if I plug in 3.0001, I see this limit should be 6. Okay? My function value is approaching 6. How do I get 6 from this? Well, we use L'Hopital's rule. I first plug in 3, I got 0 over 0. You guys got that. Well, if I take the derivative of the top and the derivative of the bottom, I get 2x over 1. And I will take the limits as x approaches 3 of 2x over 1. Well, just like we did for the first couple of limits, our first thing we try to do is plug in the value. Well, when I plugged in the value, I get 0 over 0. We'll take the derivative. Can I plug in the value now? Yes, I can plug in 3 into 2x over 1, and I get 6, which is exactly what I see here. So L'Hopital wins. The e to the 2x minus 1 over e to the x minus 1. Now, we did do the whole tangent line equation, but let's kind of use L'Hopital's, which is a little bit simpler, which is just says take the derivative of the top and the derivative of the bottom, the derivative of the top, and find the limit as x approaches 0 of this is 2e to the 2x. The derivative of the bottom is just e to the x. I then can plug in 0. I get 2e to the 0 over e to the 0, which again is just 2. Let's go to this one. Which was in the page before that one. So root 4 minus x minus 2 over x. That's in the previous page. Sorry, I'm jumping you around. Oh, it's right above, actually. Okay, it's right up there. Good. All right, well, I'm going to find it, and you guys are going to find it. I'm going to find it using my calculator. You guys are going to find it using L'Hopital's rule. Let's see if we get the same answer.
When you do the
Yep.
the exponent,
Derivative of the outside, inside left alone, times the derivative of the inside.
yeah.
So the derivative of something to the 1/2 power. All right, function doesn't look great, but I notice at 0, I don't have a y-coordinate. I'm going to plug in 0.0001, and I get -1/4. Do you guys get -1/4? Yeah. Hopefully, yes. If not, you need to work on your derivatives, people. Goodness gracious. Again, I tried. I plugged in 0. I got 0/0. I take the derivative. The derivative of root 4 minus x is 1/2 4 minus x to the -1/2 times -1. The derivative of 2 is 0. The derivative of x is 1. I can now plug this in, and I get 1/2 4 to the -1/2 times -1 is my answer. This is also 1/2 root 4 times -1. I get -1/4, just like my calculator said. Okay? Let's try this one. I get 1/2. Did you guys get 1/2? Let's see. Try to plug in 0, but we've already done this. You get 0/0. So I'm going to take the derivative of the top and the bottom. I get cos pi/3 plus x times the derivative of pi/3 plus x, which is just 1, minus 0. Sine of pi/3 is just a number. It's root 3/2. The derivative of a number is 0 over 1. I am finding the limit as x approaches 0 of this. I would then plug in 0 like I would try every single time, and I get the cosine of pi/3. The cosine of pi/3 is 1/2. Just like my calculator told me. All right. One more, then we'll move on. That one's easy. Okay. Now, this could help us for limits at infinity. L'Hopital's rule works for infinity over infinity. If I plugged in infinity, I get infinity over infinity. But we know that's not necessarily infinity. It could be infinity, it could be 0, it could be a number. Okay. Now, I would not want you to use L'Hopital's rule for this question. I would want you instead to remember how you find horizontal asymptotes, the relative growth, and the importance of the growth of functions And I'd want you to say the 2x doesn't matter, the 1 doesn't matter, that 1 doesn't matter. We're just comparing x to the 5th over e to the x. We know this is going to grow slower and this is going faster. If you think about fractions where the numerator is growing slower than the denominator and its growth, what is the fraction doing? It's getting smaller and smaller and smaller, and it's approaching 0. I'd want you to be able to just look at that and say that's 0. This one, we should recall that this is actually growing faster than the log function, which is the slowest growing function. If we have situations where we have faster growth in a numerator over a denominator, what happens? These numbers get bigger and bigger and bigger and bigger. This is trending towards infinity. But that guy right there, I'm not sure about that guy. Typically, we said if the functions grow at the same rate, that we would just use the coefficients. And you'd say, oh, well, this is a 1 and this is a 1. Is this a 1? I don't know about that guy. So this is when L'Hopital's can help us. Instead of analyzing the growth, because we are unsure about the growth, let's take the derivative of the top and the derivative of the bottom, because we will get infinity over infinity. And let's see if L'Hopital's can help us determine this limit. Remember the chain rule, the derivative of the log function times the derivative of the inside. Derivative of this log function times the derivative of this inside. I want to simplify this a little bit. Excuse me. And if I plug in infinity, I get 0 over 0. Well, it doesn't appear that this helps me. But this is screaming for you guys to do some sort of simplification, which I can do, and then get my answer. Turns out that has a horizontal asymptote at 2.
How many questions did you do? Can you be able to answer?
8. Let me throw one at you here. I want you to find the limit as x approaches 0 of the integral from 0 to x of g of t dt over x squared. And I'm going to tell you that g of 0 is 0 and g prime of 0 is 2 and g double prime of 0 is 3. Go. I plug in 0 and I get the integral from 0 to 0 of g. Well, I know that's 0. The integral from a to a of anything is 0. And I know if I plug in 0 into x squared, I get 0. So I get 0 over 0. What should I do now? Take the derivative of the top and the bottom, and then try plugging in 0. Okay, so I take the derivative. If the limit as x approaches 0, what's the derivative of this accumulation function? G of x, thank you, Mr. Navarro. Derivative of x squared, 2x. Well, then I plug in 0, I get g of 0, which is 0. And then I get 2 times 0, which is 0. So that means my limit doesn't exist. Take the derivative again. L'Hopital says, keep taking the derivative until you can plug in your value. If I take the derivative again, turns out this is equal to the limit as x approaches 0 of g prime of x times 2. G prime of 0 is 2. I get 2 over 2, which is just 1. L'Hopital's. Okay? All right, now, I've seen in a recent practice AP test a question that L'Hopital's can't help us with, that not teaching you guys the algebraic simplification methods actually hurts you guys, so we're going to be ready for it. And these are limit questions where L'Hopital's can't help. And they involve the definition of a derivative. When I first introduced you to a tangent slope generating function, we actually started out with this fancy formula. And this fancy formula is just a slope formula of 2 points that are infinitely close together. And there's an alternate formula for a derivative at a certain value that I can give you. This is the limit as x approaches c. And this, again, is just a slope formula for 2 points infinitely close together, in this case, focusing at the x location of c. Well, I have seen questions that ask you to express, or they say, hey, which one of these choices below represents the derivative of the sine function? Now, this isn't a L'Hopital's question. This is just a, do we remember the definition of a derivative, and can we use this in here? It's actually not that difficult. Let's try the sine function. First, I have to understand what f of x plus h is. Well, if f of x is the sine function, I'm just putting an x right here. Instead of an x, replace it with an x plus h. It'd be sine of x plus h. I would say that the derivative of sine would be the limit as h approaches 0 of sine of x plus h minus sine of x over h. Now, if you saw this as an answer choice, you could actually take the derivative of the top and bottom of this and discover that this derivative is cosine, and then you're like, oh, that means this must be the right one because the derivatives line up. But probably that's not a realistic thing that students would do. Maybe some of you would do that. But this is just what you may be asked to produce. Let's talk about the derivative of the log function at x equals 3. They may have you recognize that you could put it in this form. Now, the only problem is this one. I've seen students not understand how to express the derivative of this one. Let's use this form here to express the derivative of 3x squared plus 2x. Okay, Now here's the important thing. F of x plus h. Wherever you see x, you need to replace it with x plus h. F of x is just 3x squared plus 2x. So expressing the derivative of 3x squared plus 2x would be 3x plus h squared plus 2 times x plus h minus 3x squared plus 2x, that entire f of x, all over the h. Okay, you just need to be familiar with that. You're not going to see it too often. You might not see it on an AP test. You might not see it on your test. You might not see it on the midterm, but I want to make sure I teach it to you. Okay? But overall, L'Hopital's rule, just remember, you get 0 over 0, take the derivative of the top and the derivative of the bottom, and plug in the values. If you still get 0 over 0, take the derivative again, and then plug in the value. If you still get 0 over 0, just keep going. Okay? You may have to. And when we talk about the limits as x approaches infinity, you actually would end up doing that many, many times, which is why I prefer you just to understand the relative growth rates, unless you have something that seems difficult, like that log question. All right. Thank you. One on the dot.